All right, chemistry students, the last lecture for chapter 2, lecture 3. I'm doing this on a super cheap Chinese tablet that has a stylus, this stylus that I can write on, and it has, my face isn't, I don't even know if that's necessary. So you guys can tell me if you need to see my face in this video or not, but it's here for now. We'll see how this works. I do have my good blue microphone plugged into it. So this third part is talking a little bit about chemical reactions. So if we go back to when we think about the different types of representations of chemical formulas, well, of chemicals, you have chemical formulas, C for carbon, O2 for oxygen, CO2 for carbon dioxide. So now that means a reaction. Carbon reacts with oxygen in a reaction that's called a combustion. Combustion is a type of reaction where oxygen is reacted with another material. So carbon reacts with oxygen to give me carbon dioxide. So that's the symbols. If I look at that, can I move this? Yes. If I look at that in a particulate, here is a carbon atom. Here is an oxygen molecule, two oxygens stuck together, and that makes a carbon dioxide. Now check out this carbon dioxide, which is a carbon in the middle, oxygens on either side. This representation is more realistic to the shape of the actual molecule than when we saw the one that had the carbon atom in the middle, the bonds, another oxygen, and the bonds, and another oxygen. That's showing you how they're attached, but this version here is showing you more what the shape is really like. And then the macroscopic, those look like charcoal briquettes, which are basically carbon. That's what they are. And they're reacting with oxygen in the air, and they're creating flame, which is a plasma, which is actually a state of matter that's not solid, liquid, or gas. We usually think solid, liquid, and gas are pretty much the only states, but there's also plasma, and there's also something called a superfluid, which is formerly known as a Bose-Einstein condensate. There's your trivia for today. So those are our three sort of representations of chemicals in chemistry. When you, according to the law of conservation of mass, you're not going to create or destroy mass or matter. So what's going to happen is that you can't change the number of atoms of carbon or oxygen from the reactants into the products. That means the identity of the atoms and the number of the atoms stay the same. The mass also stays the same. However, the number of molecules can change because look at this. We had one, well, I'll say molecules or particles, right? Because we have one carbon here and we have one oxygen molecule here. The number of atoms doesn't change. Still have one carbon and two oxygen atoms, but now I only have one molecule. It's CO2, whereas I had two particles before, an atom and a molecule, and that became a third species, which was only one molecule. So you can rearrange them into different numbers of molecules. So the number of molecules can differ. And of course, the physical state can differ. So like look in this picture, we have carbon, which is a solid. We have oxygen, which is a gas. And when you burn it, you become carbon dioxide, which is a gas. So you can change the states. But you cannot change how many atoms there are or how much they weigh. Here is another reaction. So methane is what's in natural gas. So if you have gas piped into your house, or we have that in the chemistry lab, and you turn on the gas spigot, that's methane with some other things in it, but mostly methane. And that reacts with oxygen, and that's also a combustion. When you burn something, you're producing carbon dioxide. You're also producing water. This is why when you start up your car on a cold day, you see water coming out of the tailpipe. It's condensing. Sometimes it even drips out of the tailpipe until it gets hot enough so that the water is all vapor and not just liquid water. So a combustion is always going to produce carbon dioxide and water. if I look at this equation as it's drawn, it's a methane, which is a carbon with 4 hydrogens, right? And then I have an oxygen, which is 2 oxygens. But look over here. I have carbon, 2 oxygens. Oh, there's a 3rd oxygen and 2 hydrogens. That's not balanced. So that isn't how the reaction takes place. But if I have 2 molecules of oxygen, that says I have 2 molecules of oxygen. So this 2 down here, that says that it's an oxygen molecule. When I put the 2 as a subscript, it's saying that those are connected together in the molecule, bonded together. When I put the 2 out in the front, that just says I have 2 of those molecules. So this number is called the coefficient. The coefficient is the number that goes out in front of the species, atom or molecule. And this subscript, you can't change that, right? So I couldn't fix it by saying, oh, it's going to be O4, which would also give me 4 oxygen atoms. But that's not how oxygen comes. It only comes as 2 oxygen molecules, and they're both O2. So I can't say that it's O4. So when I'm balancing the reaction, the only thing I can change is this number out in the front. That's the coefficient. If I don't have a coefficient, then I just assume there's one of them. All right. Well, now I have 2 times 2, which is 4 oxygen atoms. 1, 2, 3, 4. On this side of the reaction, the products, I only have 3 oxygen atoms. There's 2, and there's a 3rd one. But if I put this 2 out in the front to say I have 2 waters, now I have 2 oxygens and 2 more oxygens, so that's 4. And then I have 2 times 2, which is 4 hydrogen atoms, and that matches over here, 4 hydrogen atoms. So you can change these coefficients to make the symbols match up with the particulate representation, and then my products would be a carbon with 2 oxygens. Unfortunately, I can't change colors, but there's carbon and 2 oxygens, and then 2 waters. So oxygen with 2 hydrogens, and an oxygen with 2 hydrogens. And now 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 hydrogens. There's 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens, and 1 carbon, 1 carbon. So this is the symbol representation, and this one is the particulate representation, where these are the reactants and these are the products. See how that works? So here's some examples of how they get balanced. There's this thing in chemistry, it's called the limiting reagent. It's whichever thing is fully consumed. Let me explain that by going up here. What if I have an extra oxygen? That's fine, because you do have extra oxygen, right? There's plenty of oxygen floating around. If you have an extra oxygen, it's just not going to participate. It'll just still be there at the end. So you don't write it in the reaction, but it can be there. You have extra oxygen in there. Well, which thing is then getting used up? Well, no, the oxygen's not getting used up because there was an extra one and it's still there at the end. So that means that this reactant, the methane, was what we call the limiting reactant or the limiting reagent. You can use those terms synonymously, reagent or reactant. The one that's fully consumed during the reaction, which limits the number of product molecules that may be formed. In other words, I can't make another CO2 because I don't have another CH4. I can't make any more waters, but I have extra oxygen, so that is not the limiting reactant. So that's how that works. So then there's some tips for balancing equations. I have another activity that I might post up for you about balancing equations, or maybe a Professor Dave video to just give you some practice at balancing equations. There's also this really cool simulation, and I don't always recommend them, but I do recommend this one as a pretty good simulation. You can practice looking at not just the formulas, but also these particulate representations. Just kind of play around with it for 5 minutes and see what that does for you. Here's some that you can balance. All right, you want to do these on your paper, and then in 5 seconds, the answer will appear. All right, instead of just appearing, let me just walk you through how I would do this. If I look at, this is the most complicated formula, okay? There's only one oxygen in it. There's 2 oxygen atoms over here. So in order to balance that out, I can't do this, right? That changes it. That changes it from water into hydrogen peroxide. That's not fair. But I can put a 2 in front to say that I have 2 waters. Now the oxygens are balanced. 2 oxygen atoms and 2 oxygen atoms in the 2 waters. But now I have 2 times 2, which is 4 hydrogen atoms. Oops. So if I have 4 hydrogen atoms, then I need to put a 2 in front of this guy so that I also have 4 hydrogen atoms on the left. And that would be the combustion of hydrogen. In other words, the Hindenburg, right? And then same kind of deal with nitrogen. Here I have NO2. Well, I only have 1 N, whereas here I have 2. So I need to put a 2 out in the front of that. That gives me the nitrogens being balanced. But now I have 4 oxygen atoms over here. So now I need to put a 2 out in the front of here so that I can have 4 oxygen atoms on the left side. This suggests that you should practice doing this with the particulate representations as well. So I recommend doing that also. And if you do it and see which is left over, you can figure out which thing is the limiting reagent. So I recommend doing that one as well. This one just says verify that they're balanced. So that means counting up all the atoms of each of the elements on the reactant side and verifying that they match all of the atoms of all of the products on the product side. So you can do that also. And the final couple of slides here are talking about some applications of reactions, right? So when you don't have enough oxygen to go with your hydrocarbon, this is octane, C8H18, which is a component of gasoline. It's not the octane that's on the octane rating. You might think it is, but it's not. But if it doesn't burn completely, then some of it becomes carbon monoxide. And if you don't have your catalytic converter working properly, then some of that carbon monoxide is in the exhaust. And even if it does work properly, there's still some, which is why if you turn on your car and you close the garage door and you stay in there, you're going to die from CO2, but also CO poisoning. I'm going to skip through this, but you can look at that on your own. But I did want to talk about acid rain. So sulfur is a component of coal, and coal mined in some areas has more sulfur content than coal mined in other areas. The power plants that use coal, you might know that the Asbury power plant just right near us here in southwest Missouri is just shut down, actually. When Liberty Utilities took that over, they closed it down because they decided that it would be more expedient in terms of dollars to just go ahead and stop trying to clean up their coal-fired power plant emissions and replace that with wind farms. So we've already got wind farms going in here in southwest Missouri. But when there's sulfur in the coal that burns, if you don't scrub it out with the scrubbers, then some sulfur dioxide gets out into the atmosphere. And when sulfur dioxide gets out into the atmosphere, it reacts with more oxygen to make sulfur trioxide. And when you get sulfur trioxide, it reacts with water in the atmosphere to produce sulfuric acid. Sulfuric acid, also known as battery acid. It's the acid that's in your vehicle's battery. Very caustic. We've seen since 1985, so in the last 35, 40 years, we've seen quite a bunch less sulfur dioxide emissions. That's due to shutting down some coal-fired power plants and just scrubbing their exhaust more carefully. But you can look, I just picked out a couple of examples of things that show the effects of acid rain. So here's a picture of a statue on a building from Germany before World War I. And here's the same statue in 1969. So 60-some years later, and you can see the concrete has just been dissolved away, and that's a feature of acid rain. Here's a statue of George Washington from marble, which is mostly calcium carbonate. Your trivia for this one, calcium carbonate is CaCO3, which is limestone or chalk rock, also known as, if you take chalk rock and turn it around, then you can say rock chalk. And that is limestone on which the University of Kansas was built on the hills of limestone, and it became part of their chant, right? So rock chalk Jayhawk is actually saying calcium carbonate Jayhawk. Ha, there's your trivia for today. And you can see George Washington's statue in marble before acid rain, George Washington's statue after the acid rain. So you can get nitrogen monoxide, also known as nitric oxide, when you just have nitrogen and oxygen together at really high temperatures. Well, where do you have that? In a vehicle engine, right? Because air is 21% oxygen and 78% nitrogen, and then you shove some gasoline in there and you burn it, it gets really hot, and some of this gets produced. And when that gets out into the atmosphere, it can react with oxygen to make nitrogen dioxide, and that can react with water to make nitric acid, which is also a strong acid, and it also contributes to acid rain. If you have a decent catalytic converter, then it can turn some of that stuff back into nitrogen and oxygen and reduce the nitrogen emissions, the nitrogen oxides emissions. So this slide just talks about what catalytic converters are. So a catalyst is some chemical that doesn't get used up, but just helps another reaction occur faster. And these catalysts in your catalytic converters have rare metals such as rhodium or platinum, and not very much of them, but enough of them that when the exhaust passes over them with the oxygen that's still in the air, it can help to either turn the carbon dioxide into CO2, which is less toxic, or take the nitrogen oxides and reduce them back to nitrogen. Ozone. So ozone is what is called a secondary pollutant because it gets produced from other things. Now, you can actually produce ozone, as I mentioned earlier, with electricity. Lightning produces ozone. You might have smelled ozone after a lightning strike. But ozone just gets produced in the atmosphere when sunlight hits other molecules as well. And so when some of these other molecules go into the air, it produces ozone. We think of that as a pollutant, but also it's in the higher atmosphere, like the troposphere. I think, I have to go back and check on that. It's a good thing because it blocks out the ultraviolet. We just don't want it where we're breathing it. So ozone contributing to smog in, let's say, Los Angeles is pretty toxic. Indoor pollution. So we have these days pretty tightly sealed homes. So volatile compounds that get out inside our homes stay in. In the time of coronavirus, we've been told to air things out. And the air in your house might change over, every few hours. But if you had windows open, it might change over every hour or every half an hour. You might have made accidentally some pretty toxic stuff. If you take toilet bowl cleaner and you mix it with bleach, that makes chlorine gas. Who is that nasty stuff? You better get out of there and open some windows. If you paint, right, you've definitely had some volatile organic compounds, VOCs, and you've definitely smelled those, turpentine or toluene or whatever sorts of organic compounds are in the paint. If that's your profession, you should think about wearing a mask, but not just a particulate mask, one that reduces organic vapors, or just getting some more fresh air. The very last part of this chapter is about green chemistry. So how can we do chemistry but be more sustainable? That means a way that we don't just use up our natural resources and produce less waste. So we can just use less, that's one way. But if we could use renewable resources and actually renew them, that's another way. We'll talk some more about that kind of thing later on in the class. And that's the end of this chapter. Hope you've enjoyed it. Cheers.